Okay, in the next lesson here, 3.2, we're going to be talking about differentiability. And what we're essentially getting at is, when does a function have a derivative? Okay, so under what circumstances does the function have a derivative? So we're going to first start talking about when we don't have a derivative. Okay, so we're going to start by the first one that we've talked about already, and that's this situation where we have what we call a corner. Okay, in the equation y equals radical x, or not radical x, but absolute value of x. Okay, at x equals 0, we say that we have no derivative there. Okay, and as we discussed already, okay, on the left-hand side, okay, as we're approaching 0, okay, the derivative here is -1, okay, because the equation y equals absolute value of x is just consists of two rays, if you will. One is the line y equals -x, and the other one going away is the line y equals x. So we know that on this branch we have a slope of -1. Okay, on this branch we have a slope of 1. So at 0, since those slopes where they come together are not the same, okay, we say there is no derivative at that point. Okay? So again, the left side derivative and the right side derivative are not equal. Okay? One's 1, one's -1. So, like I said, we define that situation as a corner. Okay? When the left and right derivatives exist, okay, but are not equal. So even though we're continuous at that point, okay, there's no derivative there because the left and right hand derivatives are not equal to each other. And again, we call that a corner. Now, when we look at this function, okay, this is another type of point where we don't have a derivative. Okay, it's y equals x to the positive 2/3. If we graph it, it looks as such. Okay? And that particular point, it's kind of like a corner, okay, but not exactly, and we actually call it a cusp, and here's the difference. Okay, the derivative, okay, from either side, or both sides, is -infinity to infinity. Okay, or infinity, I should say, not 2. Okay, what that means is as we approach 0 in this picture, okay, if we calculated the slope here, it would be, let's say, 5. Okay, if we go a little further, it's 10. If we go a little further, it's 100. If we go a little further, it's 142,962. Okay, the closer we get to 0, okay, the bigger the slope's going to be. Ultimately, how big does the slope get at 0? Infinitely big. Okay, same thing from the left side. We could say it's -2 here, -5, -1,000,000, etc. As we get close to 0, okay, the slope gets infinitely big. And if that's the case, then we call this a cusp. All right. Now, just for argument's sake, to help us recognize, I'm going to give you the formula for the derivative of that function. Okay. And it's this. Okay. Keep in mind, at 0, we can see if we were to plug a 0 in that, we would get no answer, okay, which would match up with what we think because there shouldn't be a derivative at that point. Okay, and as we get closer to 0, think about what's going to happen as we get closer to 0 number-wise for this derivative, and why that makes sense that the slopes get infinitely big as we get close, or infinitely small if we're going the other way. Okay, if I were to put a number like 0.000000001 into this, okay, this number on the bottom would be extremely small, wouldn't it? Okay, and less than 1, of course. And if I divide 2 by an extremely small number, what's that going to produce? A very what? A very large number. Okay, and so again, this is my slope formula, right? And so if I put in a number that's really close to 0, and I get a huge number, what is that telling me? That my slopes are infinitely big there. Okay, and the closer I get to 0, the bigger that number is going to get. True? And think about why it works on the negative side here. Okay, if I were to put a negative number in here, -0.0000, etc., okay, it's going to give me a negative number because it's a cube root. True? Okay, which indicates negative slopes, but very large numbers. True. So does that match up with what we're seeing in the picture here? Yeah. Okay. And if that's the case, then we have what we call a cusp. Now, one question we might ask is, what if we have a combination of these two? If we have one that's, say, -1 from the left, and then it goes cusp on the right, like if we have a piecewise function, okay, then we still call it a cusp. Okay. So you notice I put that here. It's the derivative from either side or both. sides, okay, is either negative infinity or positive infinity. So if we have any kind of cusp behavior on either side, okay, we call that a cusp instead of a corner. Okay? So it's only a corner if they're actual numbers, not infinity and negative infinity. All right, next. The other thing that could happen with a function is what we call a vertical tangent. Okay, if we have y equals the cube root of x, okay, that one has what we call a vertical tangent. Okay, it approaches 0, okay, it gets infinitely steep, and then approaches away from 0, okay, in this manner. All right, so that situation happens, we call that a vertical tangent, and we also have no derivative at that point. Okay, so we would say this function is not differentiable at that point. So just to practice using differentiability and differentiable, etc., you can go home when you're at home eating supper tonight, and whoever you're talking to, make sure you use those words so you can practice. All right. So, all right. So similarly, if I look at the derivative of that particular function, this is the formula for the derivative of that function. Okay. Once again, at 0, okay, notice that if we plug a 0 into that, we would get an error, true? Okay, indicating there's no derivative at 0 here. Okay. And if we plug in numbers that are very close to 0, okay, like either positive or negative 0.000001, okay, we're going to square that number, which makes it even smaller. Okay, we're going to take the cube root and multiply by 3, but ultimately we're still going to have a very small number. True? And if we divide 1 by a very small number, that's going to produce what type of numbers? Okay, large numbers. Okay, so again, is it surprising that the slopes here near 0 are very, very steep? In fact, how steep? Infinitely steep. Okay. All right. Still wondering how I got this? You got to wait for another day or two. We'll get to that soon. All right. Okay, then finally, the fourth situation that gives us a non-differentiable point for a function would be the fact that there's a discontinuity. So any of our discontinuities that we've studied, okay, jumps, infinite, removables, etc., okay, if there's a discontinuity, then the function is not differentiable at that point. Okay. Questions so far? All right. All right. So what I want to talk about next is the idea that I discussed a couple days ago. If we take a look at, illustrate that one more time for you. If we take our calculators, Lucas, we get lights for them. And we take a look at a function y equals x squared. You can do this with any function, but y equals x squared. Okay, we already know that the derivative here is 2x because we've done that with the limit definition plenty of times so far. Okay, and what I want to show one more time is that if we were to just use a standard window here and graph that, okay, and look at the point 2, 4 here, we can see that it's obviously positive. Makes sense that actually 3, I should have said 3, 9. 3, 9 up here, obviously positive. Our claim is that the slope is 6 at that point. Okay. We can verify that to ourselves by zooming. If we zoom in on said point, or close to it, and we talked earlier when I did this the first time that what seems to be happening with my curve here, instead of looking like a parabola now, it's starting to look like a what? It's starting to look like a line because we're looking at it in a very, very tiny spot, right? And one of the things about having a derivative at a particular point, okay, is that we're always going to have that property. Okay? If we were to zoom in on a point that has a derivative, okay, it should become locally linear. Fair enough? And before when we did this, we hit trace, and then we wrote down 2 points that were on this curve. Okay, and keep in mind these 2 points that we're picking at this zoom are very, very close to each other. And when we calculated the slope, okay, we found that the answer was approximately 6. So verifying what we already knew, that from our algebra work, that 6 is the correct answer when we're at x equals 3. Now, let's look at another function. If I do the absolute value function instead, which we know has a non-differentiable point, and I do my zoom 6, okay, and I try to zoom in on that, I'm going to zoom in on the origin, okay, zoomed in, zoom more, and notice that no matter how many times I continue to do this, okay, does the picture look any different? Okay. If we took points on either side of this, even though they're on either side of the screen, okay, they're super close to 0, both of them, at this zoom. Okay. But what we find is that it never becomes locally linear. Okay. There's no local linearity. Okay. So that is another indication that what's the deal at that point? There's no what? There's no derivative at that point. It's not differentiable at that point. Okay. It never becomes locally linear. Okay. All right. Next question I want to pose is: does continuity imply differentiability? Okay. If a function is continuous, does that mean it's differentiable? Well, there's Exhibit A right there. That's continuous at 0, but is it differentiable? No. Okay. So no, it doesn't. How about the other question? What if I read that the other way? Does differentiability imply continuity? Okay. If a function is differentiable at a certain point, does that mean it's continuous at that point? Yes. Yeah. Okay. Definitely. Okay. Because remember, going back up to number 4 that I had up here, okay, if there's a point of discontinuity, it's not going to be what? It's not going to be differentiable, is it? Okay. So if it is differentiable, okay, it has to be continuous. And that's actually written in theorem form in your book. It's theorem number 1. Okay. Okay, questions so far? Anybody? All right, and we're going to finish with theorem 2. It's on page 110. Well, theorem 2 tells us this is the intermediate value theorem for derivatives. Okay, and what it guarantees is that if we have some closed interval, okay, that any 2 points, okay, and keep in mind that that has to be a differentiable on the entire interval, okay, the derivative takes on every value between f of a, or f prime at a, and f prime at b. Okay, here's what we mean about that. Let's start with this example. Okay, when I have this situation where I have a derivative of 0 and a derivative of 0 at either endpoint, okay, that at some point, since the f prime at a here is 0 and f prime at b is 0, okay, that theorem just guarantees us that somewhere between a and b, okay, this function has a derivative of 0. Okay. And if you look at the function, okay, does it have a derivative of 0 somewhere in between? Yeah, in my picture, it's here. Could there be more than one place where the derivative equals 0? Sure. Okay. But it guarantees that there's at least one place where the derivative equals 0. Let's do something like this one. If I look at the slope here, let's just estimate that slope to be, let's just say it's -3. And then my slope at a half, which would be our b point in this case, looks like it's, we'll say it's not 0, we'll just say it's a half, so it's close. Okay. All right, so again, what this theorem is guaranteeing is that between a and b, if you will, again, okay, that our curve takes on every slope between -3 and 1/2. Okay. And what important slope would be between -3 and 1/2, would we think? Yeah, slope of 0. That means that at one point there's a minimum or a maximum in here, isn't there? Okay, that would guarantee this, knowing that those two facts right there. Okay, there would have to be somewhere where the slope was equal to 0. Okay, in between these two. There's also a place where the slope equals -1. Isn't that between these two? Okay, -1 is generally less interesting than the slope being 0, but still, there would be somewhere where the slope would have to equal -1. If it equals -3 at this point, 1/2 at this point, somewhere between it had to equal -1. Okay? And again, this is only true if the function is differentiable. And keep in mind that if it's differentiable, that also implies that it's continuous. Fair enough? All right, questions so far?